Well, all right. Welcome back. Today, what we're going to be looking at is section 6.3, which, as you can see here, is the section that will introduce us to replacement rules. And then 6.4 will give us the second half of the replacement rules, much as we saw with 6.1 and 6.2, splitting those up into the rules of inference, two sections. So now we're going to move on to this different kind of rule that are going to work a bit differently from the rules of inference. And so one of the things I hope to get across in this video will be just to get you to understand why replacement rules work differently from the rules of inference. I've also been able to get the slides over here on the side because I'm going to be using the board a bit more here. It gives us a little bit extra room. So with the replacement rules, as I'm saying here, they are a bit different from the rules of inference. And a key difference that I hopefully get used to as I go through this video will be that they work on parts of lines, as we will see. Now, you remember with rules of inference that they worked only in one direction, so to speak. And just to illustrate here, take our old friend modus ponens, right? When you have P horseshoe Q and you have P, modus ponens tells us that you can write down Q, right? We can validly infer Q. And so, obviously, this is working in one direction from premises to a conclusion there. Now, the replacement rules are very different, right? They, as I'm going to illustrate here, work both ways. And this is because they are logical equivalences. So they are not inferences, as we see here with modus ponens and all of the other rules of inference. These are going to be logical equivalences. And so here, just to give you a quick example, an illustration here of modus ponens in concrete terms. Just erase that real quick. Okay. All right. So if we looked at something like this, where we've got A horseshoe, B horseshoe, C, and then B is our other premise, the question is, could we conclude C from that? And I'm hoping that it's clear from what we've looked at with regard to 6.1 and 6.2, that even though you might be tempted to do it, you cannot get in here and just use modus ponens on this part of that line, right? Modus ponens doesn't work on parts of lines. The only way you could do modus ponens with something like line number 1 would be if you had A sitting around somewhere, right? Because then you would have A and A horseshoe, B horseshoe, C. And so in this case, right, the rule of inference is not working on a part of a line, but it would be working on the whole line, where A is the antecedent, and there's the antecedent again, allowing us to get B horseshoe, C, in other words, from that. So modus ponens, all of the rules of inference, they do not work on parts of lines, as we're illustrating here. So no with an exclamation point. But on the other hand, if we had a different example here, now this example, right, we might look at this, and of course the most important thing to notice about these statements is the main operator here in line number 1 would be the wedge, right? And so what we're really looking at here right, this is essentially P wedge Q, right? P wedge Q. And then here in the second line, our second premise, looks almost like tilde. That's certainly a tilde, but it looks almost like tilde P. The problem is that we have B dot A here as opposed to A dot B. And so as we will learn here in section 6.3, we're going to get a rule that will allow us to do what's called commutativity. It's going to allow us to spin the two items there around the dot. Okay, so it allows us to spin those two items around. And now, once we're able to do that, obviously this is working on just a part of line 2, right? It's just working on this interior part. Once we get this here, lines 1 and 3, this definitely is a disjunctive syllogism, right? Because we'd have P wedge Q, and then this is tilde P down here. And so that's what I'm saying there. We could use COM to make it like this, and then we could do disjunctive syllogism, which, as we'll see, is a good thing, right, in terms of using the rules of inference. So having said that, what I'm going to do here is just talk to you about these various replacement rules, the first of which is called De Morgan's rule, right? And as I'm showing you here, I'm just going to give you some written out examples of these different rules, like I did with the rules of inference. So I might say to you, not both Warren and Rubio will win the next presidential election, right? So in other words, we don't have co-presidents. We only have one winner of a presidential election. And to say that not both Warren and Rubio will win the next presidential election means the same thing as either Warren won't win or Rubio won't win the next presidential election, right? So if you just kind of reflect on the content there, the meaning in each case, they mean the same thing, right? Likewise, if I told you that neither Barack Obama nor George Bush will win the next presidential election, well, and we've seen this before, actually, back in Chapter 5, this means the same thing as Obama won't win the next presidential election and Bush won't win the next presidential election. Again, another two ways of saying the same thing. Now, let me get rid of this real quick. Takes a little while. And I'm sure you know that you can fast forward through this with the watching this on your computer. All right. So what we're looking at here with De Morgan's rule, what we're looking at here, in the first instance here, talking about Warren and Rubio, when we say not both, we're saying it's not the case that P dot Q, right? And we're saying that that means the same thing as either Warren won't win or Rubio won't win the next presidential election. Okay? So these four dots here indicate that the statement on the left means the same thing as the statement on the right. They're, in other words, logically equivalent. If you'd like, at least mentally speaking, although we don't use this symbolism in our text, but if you'd like, you can think of these as a double-headed arrow, indicating that the statement on the left is replaceable by the one on the right. And this is where the word, the replacement rules, comes from, right? The statement on the left means the same thing as the one on the right, and vice versa. So if you see one, you can replace it with the other, and again, vice versa. So this rule, De Morgan's, actually has two versions, this one here, and then the next one, as we see below, says the following. Neither Obama nor Bush will win the next presidential election means the same thing as Obama won't win the next presidential election and Bush won't win the next presidential election. So again, the statement on the left is replaceable with the one on the right. They're equivalent. And so this rule of De Morgan's has two versions, as we see here. It is complicated by all means, right? We have lots of tildes around here and dots and wedges and so forth. But I do want you to notice the pattern that's going on here. When we have a tilde out here in front of the parentheses, what happens is that that tilde gets placed on each of these interior parts, the P and the Q, as long as the dot turns into a wedge. Likewise, we have the same kind of thing going down here. We have a tilde outside the parentheses. It goes inside the parentheses with each one as long as the wedge turns into a dot. Right? So we've always got dots turning into wedges or wedges turning into dots. And that description of what's going on here works whether you're going from left to right or right to left. Because here, if we go from right to left, we have a dot, and these two tildes are sucked out here outside the parentheses. The dot turns into a wedge. Here we have a wedge turning into a dot. as well. So that's how De Morgan's works. And you just have to do your best to try and remember it. But I do want to emphasize that it is important to remember this rule because like modus ponens, right? Modus ponens is my favorite rule in terms of the rules of inference. It gets the most work done. I would encourage you to put an extra star by it on your note sheet for the exam. Well, the same here would go for De Morgan's, right? This is, of all the replacement rules, certainly one of the more important ones. And because of that, actually, as you can see here on the PowerPoint slide, I've kind of come up with a little rhyme here that will hopefully help you to remember when and a little bit of how to use it, right? So as it says there, De Morgan's rule, right? With tildes and wedges or tildes and dots, you'll use De Morgan's lots and lots, right? And so it's a bit of an annoying rhyme. I will just say it one more time here just to really bury it in your mind. And I'm doing that even though that might be painful. Hopefully in the end it will be something that's useful to you. So just remember when you're contemplating replacement rules to use when you're doing a proof, with tildes and wedges or tildes and dots, you'll use De Morgan's lots and lots. And beyond that, I would indicate that yes, you use it fairly frequently, but of these different versions of De Morgan's, I have a favorite version, and it actually would be this one here, this bottom one going from left to right. All of this is useful information, but anytime you can go from a statement like this here on the left to one on the right, it's very powerful. Let me illustrate here. So we have a statement like this, tilde A wedge B, just like that one. And from that, De Morgan says we can get tilde A dot tilde B. Tilde A dot tilde B, right? We take the tilde from the outside, apply it to both pieces, turning the wedge into a dot. And this is very helpful because once we have a dot there, that's our main operator. And now we could, for example, get tilde A by simplification on 2, for example. And then, of course, as we'll see here in a few minutes, once we have commutativity available, we'll be able to get the tilde B by itself. And once you have tilde A and tilde B, well, once you have a tilde A, you can do things with like modus tollens, perhaps, or disjunctive syllogism, maybe a modus ponens, just depending on whatever else you have. So that's a particularly useful instance of using De Morgan's. So an important rule, try to use it whenever you, again, find tildes and wedges or tildes and dots. It can be very helpful.